Great. Thank you so much for being here and for inviting me to the hosts. So I'm going to start with this slide. And what this is showing is a trajectory of current emissions today. And so the top line that you see is essentially business as usual emissions associated with CO2 and where we're heading. And so the point of this slide is to say that the old story of climate change and meeting the goals of climate change, preventing 2 degrees C or even 1.5 by 2100, have mainly been associated with avoiding CO2 emissions in the first place. And that is kind of the old way of thinking. But in light of the recent climate reports in the last year, avoiding CO2 emissions is no longer going to be enough. We have to do that, but in addition to that, we have to start taking CO2 back out of the atmosphere. And so this talk today is mostly going to be focused on how we might be able to do that using a synthetic approach. I like to call them synthetic forests, and I'm going to talk a little bit about that. I was also co-author on a study that was released by the National Academy of Sciences in January 2019. If you're interested, there's information to download it here. One of the major conclusions from this study is that in order to meet our climate goals between now and 2050, we have to remove on the order of 10 gigatons of CO2 each year. And so today, as a global society, we emit on the order of about 40. So to have to remove, not avoid, but remove 10 gigatons per year up to 2050 is significant. And further, we have to increase that to 20 gigatons of CO2 removal between 2050 and 2100 to meet climate goals. These are all of the negative emissions technologies that we outline in that report. So I'm going to specifically today talk about direct air capture, but there's others as well. The Earth has rocks that have a natural alkalinity. They're rich in calcium and magnesium that can naturally uptake CO2 from the atmosphere. We can accelerate that process. We can also use other natural solutions, such as planting trees. Afforestation means that we can plant trees on land that otherwise didn't have them, or we can do reforestation, so reforesting trees and land. So those are natural solutions. There's also bioenergy coupled to carbon capture and storage is another option, but the one that I'm going to specifically talk about today is a technology called direct air capture. And so what is direct air capture? This is using chemicals to take CO2 back out of the air. There are a lot of pros and a lot of cons to this. So some pros are it has the potential to be a negative emissions technology. The important piece there is that in order to be negative, it has to be coupled to the permanent removal of CO2 from air. And you might have read recently there was a story in Forbes that said, hey, now we can reverse climate change by turning CO2 into fuel. Not true. So if you turn CO2 into fuel by using, say, hydrogen from a carbon-free energy source, and then you burn that fuel, you're just putting CO2 back in the air. So that process is at best neutral. The only way really to couple or make this approach negative is if you take CO2 out of the air and you permanently remove it. So what that means is you have to couple it to something like geologic storage or even reactions with rocks in which the CO2 is stored for up to 1,000 years. So it needs to be stored for up to 1,000 years in order to positively impact climate. And I'll say now, because I might not get a chance to say it later, utilization is a way to deploy carbon capture plants and technologies because you can sell the CO2 for something if you're making it into a fuel or a chemical feedstock, whatever it might be. Maybe it's a pharmaceutical. You can sell that at a certain price. And today, there's not a good enough price to put CO2 into the earth. And so because of that, if we want to capture CO2, we need to be able to sell it for something in order to make it economic to build the plant to separate it in the first place. And so it's not an either or, utilization or storage. It's really about we have to do both in order to kind of go along this path. The other aspect about negative emissions, and in particular direct air capture, it's not just about removing the CO2 that's been accumulating in the atmosphere since the start of the Industrial Revolution. It's also that there are sectors of emissions that are very difficult to avoid. Transportation sector is one of them. Another one is the industrial sector. iron and steel, cement, glass making, all of these industries chemically produce CO2. So not just producing CO2 from burning of fossil fuels, but they actually chemically produce CO2. And that's a very difficult thing to avoid because you can't simply replace those processes with renewables. And so it becomes difficult. So negative emissions technologies, it's not just about pulling CO2 back out of the air, but it's also about offsetting the sectors that are very difficult to avoid. The other aspect is it doesn't come with the same negative baggage that biofuels does. Right? There's no competition for food. You don't need arable land to do direct air capture. So that's another positive. So I've mentioned a lot of positives, but there's also a lot of cons. I started in the field of direct air capture specifically about just over a decade ago, and I thought to myself, why would anybody ever do this? We should first really focus on decarbonization. We should focus on putting efforts into avoiding CO2 in the first place. But now I recognize we don't have that option. It's not that easy anymore. We have to do everything. And so cons, the energy inputs are absolutely significant. I'm going to talk about that a little bit today. In addition to the land area, you might not have to compete with food for arable land, but it doesn't mean it doesn't require a lot of land to do this. This is really the only kind of equation-related graph that I have. I'm a chemical engineer by training, and in that field, we learn a lot about thermodynamics. And when you think about taking CO2 out of air, remember it's about 410 parts per million in the atmosphere today. That's very, very dilute. The CO2 in the exhaust stream of a coal-fired power plant is on the order of about 12%. So that's 300 times more concentrated than CO2 in air. What that means is that if you want to capture the equivalent CO2 from air as you would from a power plant, your contactor area of your unit, of your device, has to be 300 times as large. And that directly translates to capital costs. It's always going to be more expensive to capture CO2 from air compared to a point source like a power plant. But the energy, and this plot is showing that, it's looking at what is the minimum energy required to do a separation. If you know the initial concentration, and you know how much you want to capture, say 60 or 90% of the stream, CO2, and you know what the final purity needs to be, then you can calculate what the minimum thermodynamic work is to carry out the separation process. And it's important because we can't do better than this. This is as good as it gets. And even as good as it gets, direct air capture will always be at least 3 times more energetic than point source capture. Again, which translates to the operating costs of doing this. The other aspect that's important here that also kind of makes the numbers in terms of costs of doing this in the literature very broad reaching. You'll see if you read this literature, you'll notice that people will quote direct air capture as costing anywhere from $50 to $1,000 per ton of CO2 removed. That's a pretty broad range, but there's reasons for that. One is that if you actually want to move the CO2 and use it for something, like maybe you're doing geologic storage or maybe you're using for enhanced oil recovery, you have to have high purity CO2 because that way it's easier to compress and be in a liquid form so you can move it in a truck or a pipeline, and that adds additional energy costs in terms of the compression. If you don't want to transport it and you want to use it on site, then you save a lot of money by not having to necessarily do all of the transportation. And you also save because you don't need such a high purity stream. So I want to do a little bit of a comparison. You might not know what the status is in the US of carbon capture today. It's actually pretty small. But this is a success story, this image that I'm showing here. This is called the Petra Nova plant. It's in Texas. And this plant is responsible for capturing 1.4 million tons of CO2 per year from a coal-fired power plant. And that CO2 is transported via pipeline for enhanced oil recovery operation there. And in enhanced oil recovery, if you don't know, I'll just say briefly, what it means is there's oil in the earth, and the oil has been stored for millions of years in the pore space of sedimentary rocks, like sandstones and things like that. And some of the oil is very difficult to extract. And so you can use supercritical CO2 in order to change the density and the viscosity and the properties of the oil, because at the conditions of which oil is in the subsurface and CO2 is in a supercritical phase, they're absolutely miscible. And so what that means is you can recover oil that you wouldn't be able to do otherwise. And the first operation was in 1972 in the Permian Basin in Texas. So we've been doing this for years, for decades, and we know how to do it. And in doing that, the CO2 is not re-emitted in the atmosphere. Ultimately, the Earth uptakes all of that CO2. And the operators of EOR, when they recover the oil at the surface, the CO2 bubbles out, they separate it, and then they pump the CO2 back in and recycle it as much as possible because they have to pay for that CO2, and they don't want to lose it. And so that's how EOR happens today, and that's how Petronova is actually storing the CO2 that they're separating from this plant. But what I want you to take from this is you notice the design of this plant. It's tall and it's thin. And then you see this image also on the left-hand side. That's what it looks like. It's a cartoon of what this looks like. And so this is a big part of what we do in chemical engineering, is designing these kinds of units to do separations. And each one of those lines that you see is a stage. What happens is you have packing material that fills this, and I'm going to show a picture of that in just a minute. You have a liquid that has a chemical in it, and that chemical reacts with CO2, but the liquid drizzles down, it's pumped actually down the packing material, and you bubble your exhaust or the gas stream up through. And as that gas is going up and up and up, it's becoming cleaner and cleaner of CO2, and that liquid that's getting pumped down is becoming more and more saturated in CO2. And then you need to heat it up, the liquid, in order to regenerate it so you can use it over and over again. And this is typically what it looks like, tall and thin. If you wanted to capture all the CO2, you would have an infinitely tall tower. We don't do that because it would translate to infinite costs. So you look at what a direct air capture contactor looks like. It's got this characteristic design. It's very long, high surface area. That goes back to what I said before. To capture the equivalent of CO2, you need 300 times the area. Why are they thin? They're thin because you want to minimize the pressure drop in the system. In other words, it takes fan power to bubble the air through. Air moves at an average velocity of 1.5 meters per second. It's pretty slow. And so we have to be able to push the air through, which means we want to minimize costs of fan power, so we have to make a thin bed. And so that's why these designs are so unique and different from point source capture. The two leading technologies today, one is called carbon engineering. And you might have heard in the news, they've partnered up with Occidental. Occidental is interested in using CO2 from air for enhanced oil recovery. And it's controversial, but there is the potential to have negative crude oil from doing this approach. And I'll talk a little bit about that later. Another company is called Climeworks. They have 14 commercial plants globally. They collectively capture on the order of about 5 kilotons of CO2 per year in all of those plants collectively. There's another company called Global Thermostat. They're not quite commercial yet, but they just partnered with ExxonMobil. And there's partnerships that Climeworks has as well. Coca-Cola, Audi. There's a lot of interest in taking CO2 from air and converting it to useful products. These are the two approaches. In the top one, you see it's a metal packing material that fills the contactor, and they use a liquid solvent similar to Petronova to do the capture. The bottom one are these honeycomb structures. If you notice how your catalytic converter looks in your automobile, a lot like this. And so you've got these kind of millimeter-sized channels, and that's what the air is going through. But embedded into the walls are chemicals, micro and mesoporous materials that selectively react with CO2. And each one of these technologies has pros and cons associated with it that impact the price. Big point here is if you want to design a direct air capture unit, which you have to do in order to estimate what the true costs of doing this are going to be, you also have to couple to it an energy plant. So to capture a significant amount of CO2, let's say, for example, 1 million tons of CO2 per year, requires 300 to 500 megawatts of power. It's significant. If you were to use coal, you emit more CO2 than you capture. If you were to use natural gas, you essentially capture, or you cut your efforts in half. And so it's very important to think about what are the energy sources that we use. If we look into the technologies that I talked about, so liquid solvents is carbon engineering, solid sorbents is more of the Global Thermostat or the Climeworks. I want to break down the capital costs versus the operating and maintenance costs, because we do this in my group to try and understand, well, where can we look at where the RD&D is in terms of improving materials or processes so we can reduce costs. And so I'm going to give you an example. The liquid solvents, there's this breakdown of capital. The way that the carbon engineering approach is they're designing really plants that capture on the order of millions of tons of CO2 per year. They're building one of those in Texas today, funded by Occidental. And so that cost of capital is dominated by the fact that they have very large pieces of equipment that aren't necessarily commercially available yet today. Large oxy-fired kiln is an example of one of those. The packing material that they use, I showed you Petronova, and I showed you an image of metal packing. Metal packing is expensive, and metal packing has very high pressure drops. So in other words, more fan power. So carbon engineering, if you look at their costs, there's about 20 knobs that you can tune in order to get the cost down really low. And it's still questionable whether or not all of those costs will be realized. One of those knobs is the packing material. They're actually looking at plastic or PVC-based material. That's a wonderful area of research, design, and development because it's still questionable whether or not it's going to perform and hold up to the caustic materials that the metal packing can. It's cheaper to make, and the pressure drops are much lower. And it's partly why you see this range, that blue, or let's see, it's the orange square. But I mean, it's partly why you see the difference in the capital for the solvent-based case is because the costs are different in terms of metal versus plastic. And it's just one example of lots of knobs that they can tune. The largest expense with the capital associated with the sorbent, in fact, 80% of the capital, is associated with the micro-mesoporous materials that are embedded on those honeycomb structures. And so that's another important factor. If we can think of ways, like thinking about chemicals like BASF, chemical companies, Dow, who can try and make these materials on a higher scale. One of the things I haven't mentioned yet is the scale of the companies that are building the DAC plants with the solid sorbents are all pretty small scale, like on the order of kilotons of CO2 per year, where the larger unit, carbon engineering, is millions of tons. So these technologies are competing at really different scales, and the capital is associated with really different sources. The operating costs primarily associated with thermal energy. In fact, when you look at the energy pie, for both of these, very, very dominant in thermal energy. But again, the technologies are different. For the solvent-based case for carbon engineering, in the end, they're actually producing a carbonate material. And so they have to heat it in an oxy-fired kiln at 900 degrees C. Whereas the solid sorbent companies like the Climeworks and the Global Thermostat, they're in that honeycomb structure. They actually only need 100 degrees C heat. So very, very different technologies. They scale different, and they have different cost parameters. So a little thought experiment. Even with all of this advanced technology, DAC is still going to cost us. Investing as a global society is essential, whether it's through regulation or subsidies or taxes on carbon. So thinking back in 1966, where the US invested about 0.5% of GDP in the Apollo program. Today, that would look like about $100 billion. And as I showed you earlier in the slide, direct air capture is just one of a portfolio of solutions. So just assume that we were to invest about 20% in direct air capture. And let's also make a big assumption. Today, Climeworks, the commercial plant that I talked about, publicly says that it costs $600 a ton to separate CO2 from air. They will also publicly say that within 5 years, they see a path to getting that down to $200 to $300 a ton. So I'm going to push it even further because it's part of what makes my job fun, and my students, have PhDs, is what if we can try and get it down to $100 a ton? If we could do that and we did make this investment, what would it add up to and what impact could it have? It would mean that we would have to plant 200 of these synthetic forests, each removing 1 million tons of CO2 per year. How much land would that take? So it depends. It's not an easy answer. It depends on what the energy source is. You could use natural gas coupled to carbon capture and storage, or maybe you want to use solar electricity coupled to renewable hydrogen. Each one is quite different. The sun, if you were to use that, has a very different capacity factor than natural gas. Natural gas, you can use it 24/7. Your direct air capture plant needs to run 24/7. If you're going to use photovoltaics, you've got a capacity factor of 40%, which means you're going to have to now invest in batteries and storage. Maybe you have to overbuild the solar. And so it's really different. That's why I said earlier, you're not just designing a direct air capture plant, you have to design the energy system to couple to it. So On the left-hand side, you can see the rough area it would take if you wanted to build 200 of these synthetic forests and remove 200 million tons of CO2 per year. It's roughly about half the land area of Boston if your energy resource is natural gas. Part of why we love the energy density of fossil fuels. Because on the right-hand side, if we were to power it with solar, it would be just over the whole size of the state of Massachusetts. So very, very different land requirements. Sure, it doesn't compete with farmland, but it still takes land to do it. Switching gears a little bit, and I'm going to touch into some of the results that we've actually generated in my research group. So one of the big questions is, if you look at, again, the 14 plants that Climeworks has today on the order of kilotons of CO2 removal per year, and then you remember the slide that I showed at the beginning of what we need to do to meet climate goals, 10 gigatons of removal per year up to 2050, 20 gigatons after that. And direct air capture is actually supposed to be part of that portfolio. But we're at kilotons today. How are we going to get from kilotons to gigatons? That's a lot of zeros, right? And we do have to move through millions of tons to get there, which is still a lot of zeros. And so in my group, what we did is we took a look at photovoltaics and noticed that in the first decade of deployment, they scaled up by about 180 times, 60% due to government incentives and policy frameworks to subsidize PV, not necessarily the technological advances that are required. And so what we did is we looked at 3 different partnerships. We looked at geothermal opportunities in the US, we looked at nuclear, and we also looked at stranded natural gas in North Dakota and Texas. And wanted to also take into account the fact that there's a federal tax credit today called 45Q that says that if you do this and you use it for geologic storage, you can get up to $50 a ton to store the CO2, and you can get up to $35 a ton if you use it for enhanced oil recovery. The state of California also has a low carbon fuel standard that's trading today at about $180 a ton. And so we looked at all of those incentives and tried to see where might beginning partnerships look like. And so here, what we're showing is direct air capture plants. Green is based upon geothermal opportunities, gray are based upon nuclear, and we're mapping it and looking at the actual transportation costs, the separation costs, the compression costs for applications of specifically EOR and geologic storage here. And I already talked about EOR a little bit earlier, and so I'm going to skip through that and get to the costs. And so for the geologic storage, the costs, depending on how you define the CO2, and there's a lot of definitions here, but if we just look at the net removed, which is the price that the climate cares about, in terms of using the stranded gas, for net removed, you can get down to about $183 for storage per ton of CO2, and a couple of hundred if you start to look at the capture associated with nuclear or geothermal. For EOR, which is kind of hard to see, but in the bottom, also a little bit lower than a couple $100 a ton. So this is very different than today's cost of $600, and that's because we're finding opportunities where low carbon and low cost heat might be available to help with this first stage of deploying plants from kilotons to millions of tons. But it's only going to get us part way, and that's why we need a lot of young people to come up with ideas to get us to gigatons, because this is really just the first step of the process. So again, back to utilization. Utilization is what's going to actually help with the economics of making the deployment of these plants work. And so what are you going to do with the CO2 if nobody's willing to pay you to put it underground? There's a couple of opportunities that I just want to mention. One is a company called Carbon Recycling International that's actually looking at CO2 to methanol, and this plant's being built in China today. There's another one looking at e-diesel, and this is Audi partnering with the direct air capture plant Climeworks that I mentioned, and Sunfire. And this is going to be a plant that's going to be built in Germany. And then there's also an interesting set of research in the area of mineral carbonation. You might have heard of this project called CarbFix in Iceland, where they're taking together geothermal, direct air capture, and basalt rocks, and they're doing direct air capture, but they're also geologically storing it in the rocks in that region of Iceland to help make, to offset electricity there, and also the CO2 that's emitted from recovering their geothermal energy. There's also a company called De Beers that are looking to be the world's first sustainable mine. And so they're looking at their mine tailings and noticing that they're high in alkalinity and can readily react with CO2 and air. And so this is another interesting opportunity that's happening with mineralization. And so looking at all of this, even with what we're doing today, all of these efforts still have to increase by 100 to 1,000 times. And I also want to mention that, again, the old portfolio is avoiding CO2, but the new portfolio has to be, we have to do everything. We have to avoid CO2, we have to fuel switch, we have to depend on renewables, we have to plant more trees, and accelerate the natural weathering of rocks, direct air capture. We have to do all of these things, and there's no silver bullet. I also want to end by saying we don't want to dismiss the impact of individual efforts. I do a lot of public speaking on this topic, and I get a lot of young people asking me, what can I do? I've given a TED Talk on this about a year ago, and I have a lot of emails from high school students from all over the world wondering what can they do to make an impact in this field. And my answer is always, you can go into the field. We need a lot more people, a workforce, whether it's an engineer, whether it's a geophysicist, whether it's a politician. We need people in this field who are invested and who understand what the challenges are. And so you might be thinking, because still somebody wants to answer the question of, well, what can I do myself on a day-to-day? So roughly, our individual emissions for living in the United States, our choices that we make in terms of energy and the cars we drive and things like that, our individual footprints in the US about 16.5 tons per person per year. And so what you see on this scale is a bunch of animals that collectively weigh about 16.5 tons. And you've got to watch carefully the screen, because what I'm going to show you is each click that I'm going to make is going to be a choice that you have every day. The first one being a very small one, whether or not you're going to use the plastic bags at the grocery store, or are you going to bring in your cloth bags, right? I mean, we're always like, I forgot my bags in the car. And so you see the smallest dog at the bottom of the scale. So it goes down a little bit if you make that decision as an individual. And so you see these other things. Well, suppose you were to plant 5 trees a year. That also can make an impact. Suppose that you were to carpool. That can also make an impact. Now we've got these 3 elephants and a giraffe. How can we make them disappear with our choices? LED light bulbs, it actually is pretty significant. And if you have, it took us like a year to finally replace all of the light bulbs in our house. It's a big effort, but it makes a very huge difference on your energy bill and the efficiency. Suppose you were to get an electric car, and be careful, because if you live in Wyoming, you're driving your car on coal. But the idea is that we're heading towards a transportation sector that's hopefully going to be pretty low carbon. Certainly if you live in California, this is a great choice. But it makes a pretty big impact to have an electric car. And this is also a significant impact if you actually choose to produce your own electricity. So obviously that giraffe was left because we all fly too much. So the idea ultimately is that climate change mitigation portfolios should include both avoiding CO2 and the removal of CO2 from the atmosphere, because both are going to be required at this late stage in order to meet our climate goals. And I'm going to end with this. I talked about thermodynamics a little bit. The back of her shirt says carbon capture and reliable storage, saving the planet, limited only by the second law of thermodynamics, which was that one slide that I showed you. And there's a group of us that meet, an international group. There's about 40 of us now. We've been meeting every year for the last couple of years. And I've been leading this effort and encouraging people to bring families. And so we've made shirts like this for all of our group. And it's important to remember why we're spending so much energy working in this field, because it's the legacy that we want to leave. We don't want to leave all of these issues that we hear about with climate on the shoulders of our kids and grandkids and their grandkids. And so it's an important topic. And right now, this group that I'm working with, we're actually trying to make a CO2 primer on negative emissions to try and make it so that everybody can kind of understand and speak the same language. And we just launched this summer an open access journal, the first one on negative emissions technologies. If you want to take a look, it's called Frontiers Negative Emissions Technologies Journal. And it's an interesting set of papers that we've just released this summer. And so with that, Thank you so much again for having me. Thank you.